Hello, everybody. Welcome back.
Hello.
Hello.
Hello. Good to hear you.
Hi.
Hi. Good. All right. Today's November 23rd, 2020. Oh my God, this year's almost over. Can't believe it. All right, let's start with attendance and get started. Start like from the middle. How does that sound? Amanda.
Here.
Okay. Steffi.
Here.
Christina.
Here.
Then Naja.
Here. I'm sorry.
Morgan. Gianna.
Here.
Apurva. Emma. No Emma? Okay. Samantha.
Here.
Jenny. No Jenny. Okay. Joy.
Here.
And then Alexis. No Alexis. Okay. Abby.
Here.
Laura.
Here.
Deidre.
Here.
Ashley.
Here.
Paulina.
Here.
Akili.
Here.
Liam.
Here.
Emily.
Here.
Mara.
Here.
Savannah.
Here.
Carrie.
Here.
Jameslyn.
Here.
Apurva. I see you on the, as a little block. Yeah. Okay, perfect. Last call for Apurva's here. Last call for Emma. Are you here?
Emma was getting her wisdom teeth out today.
She might have sent an email. Okay. Yes, that's right. And then do I have Samantha is here? Yes. And then Jenny, are you here? And what about Alexis? No? Okay. No Jenny, no Alexis. Okay. All right. Welcome back, guys. Felt like a little bit of a long weekend for me. I don't know about you guys, but let's see if you guys remember. So we started a new topic last week. Hopefully you remember. Who remembers what we talked about? Let's see how much we remember.
The hypothesis. I forgot the last part, but I remember the formulas.
Yes, hypothesis. I mean, that's pretty much what we were talking about. We're talking about hypothesis, and in particular, the phrase we've been dealing with is hypothesis testing. Okay, so let's start with actually hypothesis. It's a very important word in that. What is a hypothesis, guys?
A prediction based on a correlation?
Interesting. We haven't covered correlation yet, but we will. That is our next topic. Good job, Morgan. So we have sorry?
A claim?
It is a claim. Very good. Okay, so we haven't talked about correlation. It's a very, very important topic. We'll talk about that next. That's our next topic. But it's a claim, right? We're saying a statement, okay? What are we making a claim about, guys? What kind of statement are we making?
It's a claim about the population parameter.
Very good, right? So again, I think for maybe the 100th time, usually and most typically, you will not have access to the population information, right? The population parameters. And that parameter could be the mean, the variance, the standard deviation, whatever statistic, whatever number it is, whatever information it is about the population, usually we don't have access to that, right? but we are curious beings and we want to know about the population because that's the entire picture, right? It doesn't get bigger than that. That's the whole picture. Since we don't have access to that information, we like to kind of guess, right? Preferably an educated guess. And one way of doing that is to make a claim. We make a hypothesis. We hypothesize about the population. And in particular, we've been focusing on the population mean, which is probably the only thing we'll focus on, right? We believe the population mean will be blah, 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 blah. And this is not a new concept for you guys. We've been kind of guessing the population mean, right? And one way we did it was that we think this is the population mean, but then we kind of stepped back and said, well, you know, just like pinpoint the population mean to be a specific number, that's pretty bold. So what we're going to do is we're going to take a step back and we're going to say, well, we believe the population mean will be between these two numbers, right? So that was the upper and lower and upper bound, which was confidence intervals, right? So we like this whole semester, we've been talking about population parameters a lot. And we are trying to get to that. That's kind of like the gold mine, whatever, right? So we're trying to get there, and we've been using different kind of methodologies to get there, right? First, we kind of like pinpoint it exactly, and we say, well, if we like take a sample and take the average, you know, the mean, and plot that, well, that sample mean is going to align with the population mean. And that's pretty good because if you do the sampling enough times, repeat that 10,000 times or something, it does show that based on the central limit theorem, that it will approach the population mean. However, that's like, you know, you really need to repeat that a lot, and that's usually done in simulations, right? In real life, that's a hard thing to achieve. We did that in Rock and Pole Station. They repeat the things over and over and over again to get to a more accurate result. We saw that in the videos where they're talking about the diseases, and you have to repeat the experiment over and over and again, right? So guessing the population mean to be some exact number we have done, but it's like not very practical. So then we take a step back and are like, well, we think it's going to be between this, like 95% of the time we're confident about that, right? Now we're taking another different approach to do the same thing, where we're still trying to predict, as to use Morgan's words. We're trying to predict, we're trying to make an educated scholarly guess and what the population parameters would be, specifically the population mean to be when we have limited information. So we're going to go ahead and hypothesize. We're going to say, well, we believe that this, the population mean is this, a specific value. How do we test that hypothesis? Well, we do something called hypothesis testing. And that's one of the methods that we're learning last week and this week to see whether this claim that we make about the population mean is actually like a legitimate one, or it's like not so good. So then we want to reject it. Okay. All right. So that's the kind of like overall overarching goal. So within hypothesis testing, we haven't finished all the steps, and that's what we'll do today. But we did focus on one step, the first step. And who remembers what we did last week specifically? There's about 4 steps. We haven't covered second, third, and fourth, but there's a very first step we practiced a little bit. And we did that with the, you know, the Word document with a handout, and we practiced a few questions together.
The null hypothesis and alternative hypothesis.
Excellent, Christina, right? We set something up called the null hypothesis, and then an alternative hypothesis. Okay, who can elaborate on what a null hypothesis is and an alternative hypothesis is?
The null hypothesis is, I mean, it can be written as like capital H and then like a small like 0.
Yes.
And it states that the parameter of interest is equal to a specific value.
Very good. Anybody? Very excellent, right? We denote it as HO, O symbolizing the null, H symbolizing the hypothesis, and we say that the population parameter, again, for our purpose, we're probably only going to deal with population mean. So the population mean equals some number. That's usually how we want to set the null hypothesis. Very good. What about the alternative hypothesis? Anybody?
The alternative hypothesis is usually, it's like something different. So it could be like the population mean is less than, greater than, or not equal to.
Very good, right? So we set the null hypothesis to be equal to a specific value, right? Mu equals something. And then the alternative is literally the alternative of that null. So it can be less than or greater than or not equal to. Very, very good. Okay, so we set up the null hypothesis and the alternative hypothesis, and it's for a specific reason. What do we want to do with these hypotheses? Like, what do we favor, if you will? What we want to achieve, do we set that inside the null or do we set that inside the alternative? Anybody?
The alternative.
Yes, we want the alternative hypothesis to be true. As in a lot of things in science and math and logic and stuff, it is always hard to prove something that it's always true, right? Because you give one counterexample, then that whole hypothesis or that statement or that claim is gone, right? So what we do is kind of like, in order, since that's so difficult to achieve, we kind of take like a different route, which is this whole null hypothesis idea, right? So we set something, the mu, to be something that we believe it's not, right? So then what we can do is, since it's easier to give an example of when it's not the case, then it's easy to disprove the null hypothesis. So the goal, as far as you guys are concerned, is that we want to provide enough evidence that we can confidently reject the null hypothesis. And in that case, and if we have a really high confidence of rejecting the null hypothesis, then it's very likely that we can accept the alternative hypothesis. So the way we conclude, which we will get to today, is that you either reject the null hypothesis or you fail to reject the hypothesis, okay? And particularly, to be a little bit more detailed in terms of rejecting it, you can kind of like mildly reject it, you can just reject it, or you can like strongly reject it. So we'll talk about the nuances of what that means. But basically, it's kind of like how much evidence you have to reject it. Like you're like really confident that pretty much like there's no way the null is true. That's a good place to be. Then we can really comfortably accept the alternative hypothesis. But if we don't, like, we're pretty sure, but like not like, I won't put my life on it kind of sure that we can reject the null, then it's harder to accept the alternative hypothesis, right? And all things in life, as you can imagine, they're all always on a spectrum. So this one is too, and we're going to talk about those different kinds of conclusions. And that is kind of where we're going as the goal for hypothesis testing. Okay, so as an overall concept, are we good? Any questions? Any things that I forgot to review? No, yes, no. Okay. So let's see. Are we still missing Jenny and Alexis? Nobody? I know some people are kind of coming in and out. The challenge of Wi-Fi. Okay, so what you should do is everybody go to Blackboard. And then the usual content. And then we're still in hypothesis testing. There should be only one folder that has the phrase hypothesis testing. Go into it, and there should be a file or a link that says, let me go into it and give you the exact title. It's below the HT for means handout submission. It's right, it says hypothesis testing -means mini lecture. So that's going to be a Google Doc that you have viewing privileges for, but you can't edit it. So if you want to edit it and take notes inside that, I would recommend that you go to File and save a copy in your drive. but it's just a relatively long document. And we're gonna go through that together to finish up all the steps of hypothesis testing for means. And then we are going to solve a few problems together, okay? And then you will have some homework to continue practicing these problems. All right, I see that a bunch of you guys have logged in. If you have this ready, I would recommend just go ahead and make a copy so you can take notes as we talk about this. And then once you have made a copy and you're ready to take notes, type in ready in the chat for me. So I know you guys are there. Excellent. 1, 2, 3, 4, 5. Good, good, good. What's going on today? My usual, let's see, Morgan, Christina, Mara, Steffi, and Samantha don't have their cameras on. Today's not a good day, not a good facial day. Hello, see, isn't that nice? This is
I
not.
was folding laundry while you were doing attendance. I didn't want you to see that.
That doesn't mean the rest of you guys don't have to put your cameras on. I'm encouraging you to. So that didn't seem to really work this semester. I told you about that ridiculous thing that happened in my other section, right? That they were realizing they were in the same class and they're like, oh, you're that person. And I was like, oh God. I was like, you're welcome. As they're talking about how they're very disturbed that their professor doesn't turn their camera on, they're like, it's really weird. And I'm like, how do you think that makes me feel? And still during that whole conversation, everybody had their cameras off. I'm like, I mean, if I'm defining irony, would this be it? Anyways, I'm gonna have I'm like kind of like the social chair of my department. So I'm hosting a virtual happy hour with our department chair people, and we're supposed to bring our best COVID stories. I'm totally sharing that with all of them. I was like, let me teach you what the word irony means. Let me begin. That's how I told them to bring their best stories. You guys, as you can imagine, the whole school, like the biggest topic we talk about these days is how do we get the cameras to be turned on for the students? All right, understood, Savannah, I hear you. Don't worry, Deidre, it's fine. I know a lot of you guys are having Wi-Fi issues. Yes, correct, Samantha. Hypothesis testing dash means mini lecture, okay? So go ahead and make a copy for yourself so that you can take notes because you might want to. Let me zoom in and then I'll share my screen. I realize that I have this beautiful extra screen, so when I share, it's gonna be nice. Okay, maybe I can even do 200%. Oh, this is why you get a big screen. Nice. All right. Okay, so let's get into it, guys. Okay, and we go through the whole steps, and then solve some problems together. All right. So let me share my screen. Okay. Oh, and then let me bring this over here, and then I got to change the orientation of this so I don't get confused. Okay, and then I will have my chat open. So if you want to like chat me something. All right. Okay, here we go. Okay, hypothesis testing, guys. So this is kind of like what we've been talking about, right? Hypothesis testing helps to think, it helps to think of hypothesis testing as seeing if a claim someone makes is true, right? As Carrie said, it's a claim, right? We're trying to make a statement. A hypothesis is a claim put forth by somebody, right? If the calculation from our sample leads us to believe the claim is true, we accept it. If not, we reject it. In our particular case, we hope to reject the null hypothesis, okay? All right, so this is an example we're gonna kind of follow. It's not really that big of an example, but back in the days when Zappos had VIP, let's say Zappos claims that the average shipping time is 1 day, okay? And we are going to refer to this particular claim as the hypothesis, okay? That's the claim Zappos is making, and we want to see if that claim is actually legitimate or not, okay? All right. So this is what we're going to talk about. So in that situation, we are going to define the null and what the alternative hypothesis will be. Okay. HO, as we've been talking about, as Christina also pointed out, Samantha and Christina pointed out, HO is called the null hypothesis. And it says that the population mean mu is equal to some specific number. So this like kind of doesn't look like obviously a specific number, but this is kind of abstracted. So this, you can just think of this as some value, some number, okay? We just wanted to kind of like make it look different from the mu. So we call it mu0, okay? But just, this is a number. Mu equals some number. The other hypothesis is called HA, the alternative hypothesis. And yes, it is either less than or greater than and different than something, as Naja pointed out, right? Okay, so this is what we know. And based on that, we are going to use this Zappos example and kind of set it up. So what you will do is that specific number, mu0, is going to equal 1. Because the unit we're talking about is days, right? How many days it takes to ship a pair of shoes or something like that, right? We believe, or Zappos believes, the shipping, it takes only 1 day. As you can kind of see that setting this up as a null hypothesis, we kind of believe that's not true. We believe the shipping duration is probably, you know, not, at least not equal to a day. Probably we think it's more than a day, but let's say we don't have that much information. We just kind of believe that this is not going to be true. We have a suspicion, like a little suspicion that this is not necessarily true. So as an alternative hypothesis, we'll stick to maybe the mu does not equal to 1 day of shipping. All right. But as you know, depending on the context and what the question is asking, and you guys might remember this from the Word document from the M&M fun packs, right? It might not give you enough information and just say, they might just say something like, well, we think it's different than 17 M&Ms. Then it's just not equal to. But if it says something like, well, the researchers or the customers believe that there's less than 17 M&Ms per pack, right? Then in that case, you want to use one of these specific ones, less than, greater than, right? So it depends on the context that is given to you that you would choose one of these 3 alternative hypotheses, okay? All right, so one other thing that you need to know is that when it's greater than and or less than, we are dealing with a one-tail test. Okay, one-tail test, and that's either a left tail test and a right tail test. And you might be like, I don't really know what that means, but you guys kind of do. So I'm going to scroll down a little bit down here because there's some visuals, if it actually loads up for me. What we've been doing in anything that related to the area under the curve is a one-tail test. So a one-tail test basically looks like this, right? Literally, it has one tail that is shaded. Okay, so this in particular is a right tail test. It says right here, right tail test, but there's only one tail. So therefore it's a right tail test and it's also a one tail test. And this is also a one tail test. And this tail that's colored in maroon or something is on the left side. So it's a left tail test, okay? So if we're only dealing with area under the curve on one end, then that is considered a one tail test. As you know, from the options for the alternative hypothesis, we have something that's called, we have a situation where it's just different than the null hypothesis value, then that's called a two-tailed test. And as you can imagine, you might have this normal distribution, and we're going to have two ends, the two tails that are colored. And so that's going to be considered a two-tailed test, okay? And we'll get to that, right? Just kind of like consider that depending on this arrows and these symbols, we might be dealing with a one-tailed test versus a two-tailed test. And this will become obvious later why this information is important, because it basically, we kind of use a different equation depending on that. Okay, so these are the options of null and alternative hypothesis. As in, there is a null, and then we have maybe possibly 3 options for the alternative hypothesis. Okay, so let's practice identifying the null and alternative. Okay, so for the Zappos one, we kind of did it, right? It's the null is mu equal to 1, and the mu, the alternative HA would be mu doesn't equal to 1. Okay, so right now on a piece of paper or in your Google document right now, let's do number 1 and number 2. Let's see what you come up with a null hypothesis and the alternative hypothesis. Okay, so usually what you want to do is you want to have HO, like maybe colon, and then mu equals, and then HA colon, and then mu whatever symbol, and do that. Okay, so try number 1 and try number 2. Let's just do 2 for now and see if we kind of remember what we did last week. Or you can, you know, if you have like a notebook like me and a pen, you can do that as well. But what I recommend is that, you know, you have all your notes in one place. All right, what do we have for number 1? What do we have for null and alternative? Anybody?
I said the null is equal 60, and then the alternative is the mean is greater than 60.
All right, so Savannah has that. Do people agree or do people have something different? Christina agrees.
I'm a little confused on when we're using the mu0. I don't.
Oh, mu0 is like, in this case, it's 60. It just is a symbol.
Oh, okay, so we don't have to.
Yeah, you will never
Okay.
actually be using that symbol. That was just so that, you know, when they write it, you know, they don't have a specific value because they're not dealing with a specific problem. So that's kind of like a placeholder for a specific value. That's all it means. All right, yes, Emily agrees and Jenny agrees. Okay, very good, right? I would have done the same thing. I would have been like mu equals 60, and then alternative, I would have done mu greater than 60. Okay, very good. What about number 2? Who's got null and alternative?
I got the null is 2.5 and is equal to 2.5,
Mhm.
and the alternative is not equal to 2.5.
Okay, so that's what Samantha has. Anybody like, I agree, disagree, I have something different, I got the same?
Question. So the alternative is never equal to correct? Because based on what I'm like seeing, it's like the null is always equal to what we're given, but the alternative is never. Is there ever a case when the alternative will be equal to it or no?
As far as my experience goes, your suspicion is correct. I have never seen an alternative be like something equal to. Correct.
Okay.
Yeah, very good. So Mara agrees, Deidre and Savannah agree. Okay, good. I would have done the same thing, right? The mu equals 2.5, and the alternative will be mu does not equal to 2.5. Okay, very good. So there's another question below you can practice with, and then it also, if you scroll down, you can see that it actually shows you the answers for those 3 questions, right? So you've got plenty of experience, I feel like, from last week and this week. You're kind of getting a gist of what the null and alternative would look like. And James Lynn pointed out something very important, that you will always kind of have mu equals something that is kind of written in the definition, right? Mu equals a specific value. And that's that symbol mu0 that's kind of like just a placeholder that Morgan was asking about, right? It's always going to equal some specific value. And the alternative is going to be what the null is not, in one form or another, in particular 3 different kind of forms, okay? So that's what we have, okay? All right, so now that we kind of like are done with that, we're going to look at a specific problem, and then we're going to walk through the rest of the steps of hypothesis testing and come all the way to the conclusion, okay? So we're gonna slowly do that. Okay, so if you click on this that says start here, you're actually gonna open up a Google's book thing. And I realized later on, maybe when my Wi-Fi was better, you can see it better. But I didn't know that it actually would load like that. So I actually just have the A, B, C, D questions inside this document. So I took a screenshot. It's not great, but you can still read it. So this is the questions, okay? So let me, if I can, Liam, can you read that question for us prior to?
I'm sorry, where is that?
It's on my shared screen, or if you want, there's a link where it says start here. And if you click on that, it will open up a new tab and it'll be in a Google's book thing. And it's that question 20-9 basketball scoring.
Okay.
Yeah. So
Prior to the 1999-2000 season in the National Basketball Association, the league made several rule changes designed to increase scoring. The average number of points scored per game in the previous season had been 183.2. Let mu denote the mean number of points per game in the 1999-2000 NBA season.
Thank you. Very clear. Okay. So I don't watch enough basketball to know if this is actually true or not. Maybe some of you guys do know, but let's, maybe this is based on true facts. So prior to this season, they always kind of calculate how many scores the players are making, I guess. And the average was 183.2, but they wanted to increase the score, right? After this season, right? Following this season. So they made some rule changes, apparently. Okay, so this is the information we have. So A is, if the rule changes had no effect on scoring, what value would mu have? So in other words, could this be the null hypothesis? What do you guys think? So this is kind of like a very contextualized problem that you may or may not see. So it's not as clear as this is a null. So Mara and Morgan say yes. Okay, very good, right? So the whole purpose of changing the rules is so that they see an increase in score. So the null is going to be that the mu is equal to 183.2, basically stating that the changing of the rules, before and after the changing of the rules, the score stayed the same, meaning that the changing of the rules had no effect whatsoever. That is the null hypothesis. And we purposely, or the NBA purposely, change the rules so that there is a difference. So what we want to see is that there is a score increase. So that will be our alternative. So the null is definitely mu equals 183.2, right? The same value. So this is A, mu equals 183.2. Sorry, okay. So then if the rule changes had the desired effect, and this is your job to figure out what the desired effect is, right? So you'll go again and read the question again to see what their intention was and what they actually wanted. And then that desired effect could be, this is kind of asking what it is, but we already know the desired effect should be the alternative hypothesis. So what would you guys say the alternative hypothesis is? Excellent, right? the rule changes was designed to increase the scoring. So as Savannah, Jenny, and Morgan said, we want the mu to be greater than 183.2, right? Because that means after the rule changed, the score actually increased as they intended. Okay, so that will be B, and this is the alternative hypothesis, right? Very good. All right, so C is, we're gonna use use some kind of technology to examine the visual displays of this distribution. So what the following sample data are shown here. So 1, 2, 3, 4, 5, and there's a total of 25. So this could be given to you in a problem too, right? So what you would normally do is you would write these numbers inside a Google spreadsheet in each cell. And this is the data of the scores after the rules have been changed, okay? So now we're actually gonna use real data to test whether the average is greater than 183.2 after the rules have been changed, okay? So I went ahead and kind of did a dot plot for you guys, okay? So look at this dot plot. If you were to just look at it, and let's say you don't have other information, and let's say this is 184, so 183.2 is probably somewhere around here, where my cursor is, right? This like little thing, arrow thing. So if I were to kind of like pretend there's like this line here, there's an invisible line around here. This is the mu, right? Before this, before the rules have been changed. Just looking at the dots, because each dot represents one data point. What do you guys think? Just a wild guess. Did the scores increase? Savannah says yes, right? Because immediately, and Steffi says yes, immediately, just roughly speaking, there's 1, 2, 3, 4 points that are below 183.2, and all the rest of the dots are above that. So that's also a kind of a good indication to be like, yeah, probably the scores on average increased after the rules have been changed, okay? So this is kind of like a visual way to confirm your hypothesis and be like, okay, this is an alternative, that's a good claim to make, okay? And then this is another way of visualizing it, right? So 183, let's just pretend it's kind of like somewhere over here. You can still see that as well. All right, overall, it looks pretty bell-shaped with some outliers. It has many points above the 183.2 score. So looking at the displays shows visual evidence of an increase in the points per game scored after the rule has changed, okay? Or after some of the rules have changed. All right, so I'm just giving this to you, but what you could do if the question just gave you this much, as I said, you would put this in a Google spreadsheet, and maybe or maybe you don't remember, but remember you can find out the sample mean, right? You just do equal average, and then you select all those 25 cells. And then also you can also find the sample standard deviation if you do equal STDEV and select all the samples that are given to you, right? So if the question doesn't give it to you, as in the sample mean and the sample standard deviation, then you would calculate it yourself by selecting all the cells, okay? Here, I provided it for you. Okay, so that's what you will use. You will eventually use to continue with the hypothesis testing, okay? All right, so let's actually talk about what steps you will go through to either reject the null hypothesis or fail to reject the null hypothesis. Okay, so number one, we are like now fully familiar with. Set up the initial conditions. That's the part where you set up the null and alternative hypothesis, okay? Then second part says take a random sample and compute the test statistics. So take a random sample. You will never do this by hand. This will be given to you in the problem set, okay? Either it's going to be given to you like the MBA problem where they give you like 25 random samples, or they don't tell you the raw data of the sample, but they just summarize it with giving you the sample mean and the sample standard deviation, okay? And then we are going to use something called the test statistic, which we'll discuss in a second, okay? And this is basically where you're gonna plug in numbers to calculate something. Specifically, it's called the test statistics. And then with that test statistic, again, you will be plugging in numbers to find the p-value. The p-value is equivalent to area under the curve, Okay, so when you hear p-value, you're always going to think, area under the curve, either left tail, right tail, or two-tailed. Remember that thing we briefly mentioned? So it's going to be one of those. So just think of shading an area under the curve. That's what you're finding for p-value. Okay, so technically this computing the test statistic and finding the p-value is actually a very familiar territory for you guys, because calculating the calculating the test statistics is the same thing as either getting the Z critical value or the T critical value. You might remember that right before midterm 2, we covered that. That's what calculating the test statistic means. And then we calculate the p-value, as in we'll get help from Google spreadsheet or whatnot. That's area under the curve. So basically number 2 and number 3 are exactly the same kind of steps we've been taking for a lot of the things that we've done in this class, okay? And then from that, we're just gonna state the conclusions, okay? And that we will learn how to do. And that basically is reject the null hypothesis or fail to reject the null hypothesis. And we don't end there. That's kind of like the abstract conclusion, but we want to always contextualize our conclusion. So for example, for the Zappos example is that, let's say we rejected the null hypothesis, then we say that we have evidence to support that Zappos delivery time is not 1 day. Something like that. So in that particular context of the problem, we will further explain or infer what rejecting the null hypothesis or fail to reject the null hypothesis means. Okay, so that's the end of the hypothesis testing. That's what we're doing. Okay, so to go into a little bit more detail, set up the initial condition was a null and alternative. Take a random sample and compute the test statistic will mean you will be, a lot of times you will be calculating the T critical value. And this is the equation that we did cover in our textbook Mathplosion. And that Morgan, to be this thing mu0 is, we don't have a number yet, but that's the number that you set up in the null hypothesis. So that's what it means, right?
It's like a variable.
Correct.
Basically,
Correct.
yeah.
So it's X bar, which should be given to you in the question, or you calculate the sample mean, and then you subtract what you set up as the null hypothesis, and you divide that by the sample standard deviation divided by the square root of n. And the n also should be given to you. The s should be given to you too, right? But all of this information should be given to you, so you just plug it in. Or, you know, we can use the Google spreadsheet to calculate it immediately. But in one way or another, you are going to calculate the critical T. If you remember, we were using T inverse, T, I, and V to get this number, okay? But I'll show you again how to do that. All right, from that, you are going to calculate the p-value. And then this one, you can also, I'll show you, we'll go through this. We can use Google spreadsheet, or there's a website where it will calculate the p-value for you and you're plugging in numbers. But it's exactly the same. It looks different, but it's exactly the same what you would do in Google spreadsheet. Because Google spreadsheet, you're going to do equal t dist, and inside the parentheses, you're going to put in 3 numbers. This p-value calculator, go ahead and click on it. You can click on it and I'll show you. I'm showing it to you right here. You're going to put in the t-score. This is the one we just calculated. And then we're going to do this thing called degrees of freedom. You might remember that. We briefly talked about it. And you're going to click one-tailed or two-tailed, and it's going to calculate it. This is 1, 2, 3. These 3 pieces of information is what you will enter in the Google spreadsheet equation as well. So it's exactly the same thing, just looks a little bit different, okay? We'll walk through that in a second. So that's how you will get the p-value. And remember, p-value means area under the curve, okay? So then with that p-value, you are going to go to your last stage of hypothesis testing, which means you are going to make a conclusion, okay? And really, there's 2 conclusions. There's you reject the null hypothesis, or you fail to reject the null hypothesis. However, there's kind of like 5 nuanced ways to reject or fail to reject the null hypothesis. And so the p-value, whatever you get, and it will be a specific number. P-value is going to be always between 0 and 1. You will get some number, and then you can compare it to these ranges, and then you could say something like, well, there's not a lot of evidence against the null, so I can't reject the null. And then the other 4 is all under the big umbrella statement of rejecting the null. You have some evidence to reject the null, a moderate amount of evidence to reject the null. You have strong evidence to reject the null, and then you have very, very strong evidence to reject the null. And we're going to talk about this p-value in a second, okay? So the p-value is going to be a number between 0 and 1, and basically the smaller the p-value is, the better it is. And the better it is, meaning that you have more evidence to reject the null hypothesis, because that's what we want to do. We want to reject the null hypothesis. Okay, so that's the gist of it. It's still a little foreign. This concept is a little bit foreign in terms of the p-value, and like how to reject the null or not reject the null is a little bit new. So what we're going to do is first we're going to look at a little clip about what p-value is, and hopefully that will give you a better idea of what the p-value means. And then after that, we're going to walk through the steps specifically together. Okay? All right, here we go. It's hopefully my internet is going to be okay. All right, here we go. So this is p-value explained.
A p-value is an abbreviation of a probability value, and the p-value is a number that can be any value between 0 and 1. But what exactly does this number represent? The official definition of a p-value is quite difficult to understand. A p-value is the probability of obtaining the observed difference, or a larger one, in the outcome measure, given that no difference exists between treatments in the population. So, the best way to explain what a p-value is to use an example. Let's say you want to perform an experiment to see if a new type of weight loss drug, drug X, causes people to lose weight. So, you randomly sample a collection of volunteers and randomly assign them into 2 groups, Group A and Group B. By the way, if you don't know the difference between a sample and a population, it might be worth checking out the previous video. You give Group A a placebo. In other words, this contains no active ingredients. Group A are therefore the control group. And you give Group B the new drug, drug X. The participants are weighed at the start of the study and at the end of the study, and this way you can work out the body weight difference. At the end of the study, you work out that Group A's average body weight difference was 0 kilograms. In other words, they did not gain or lose any body weight. Group B's body weight difference was negative 1 kilogram. So on average, they lost 1 kilogram of their body weight. So does this mean that the drug worked? To determine this, we first ask ourselves, what would happen in a world where the weight difference in volunteers who received drug X is the same as the weight difference who received the placebo? This is...
So you can see the company or whatever is gonna want the drug X to work, right? Assuming that then they'll sell it and it'll be profitable. So as the null, they're gonna assume that the drug X had no effect, so they can see if they can reject that null, okay?
It's where the null hypothesis comes in. Usually, the null hypothesis states that there are no difference between groups, for example. So, our null hypothesis is that the weight difference in those who receive drug X is the same as the weight difference in those who receive the placebo. Now we can ask ourselves, if this null hypothesis were true, what is the chance or probability of discovering a 1 kilogram reduction or more in body weight in those treated with drug X from our sample? This probability, or p-value, measures the strength of evidence against the null hypothesis. And you can think of this as a court trial where the defendant is innocent until proven guilty. In this case, the defendant is the null hypothesis. The smaller the p-value, the stronger the evidence against the null hypothesis. To determine the p-value, scientists use what are known as statistical hypothesis tests. Common examples include the student t-test and a one-way ANOVA. Since this is a top-line overview, I will not bombard you with statistical jargon, but instead pretend we have performed a statistical test using our data. So after inputting our data into a statistical test, we get a p-value in return. Let's say, for example, the p-value is 0.02. It's worth mentioning that the p-value is a fraction. However, it may be easier to convert this to a percentage to simply understand the concept better. So a value of 0.02 would be 2%. I simply multiplied the fraction by 100. But what does this p-value result of 0.02 or 2% actually represent? Essentially, this means that if the null hypothesis were true, in other words, that the two population means are identical, then there is a 2% chance of observing a difference as large or larger than what we observed in our sample. In our example, this would translate to, in a world where the weight difference in those who receive drug X is the same as the weight difference in those who receive the placebo, then there is a 2% chance of observing a weight loss of 1 kilogram or more between our sample groups. To put that into perspective, a 2% chance is 1 in every 50 experiments. But how can this be? What is accounting for this 2%? Simply, this 2% can be accounted for by random noise. Let's elaborate a bit more on random noise. There are quite a few things that can impact the p-value, and some of these factors are collectively known as random noise or random chance. One type of factor that can contribute to random noise, especially in human studies, is the coincidence of random sampling. For example, humans can exhibit a large amount of variation between one another due to genetic and environmental influences. If we relate back to our example, some humans may contain an unknown gene that speeds up their metabolism and causes them to lose weight more than those without the gene. When recruiting volunteers for our experiment, we did not perform any DNA analysis before randomly assigning the volunteers to either Group A, the control group, or Group B, the drug X group. So there was no way of knowing who was a carrier of this gene or not. So imagine a situation where, just by pure coincidence, more volunteers with the high metabolism gene are placed in Group B compared with Group A. So you can see that this scenario favors Group B. Ultimately, you can see that just by pure coincidence of random sampling, this can have a knock-on effect on the p-value. So to sum up, a p-value is a value between 0 and 1. This p-value represents the probability of obtaining the observed difference, or a larger one, in the outcome measure of the sample, given that no difference exists between the treatments in the population. In other words, when the null hypothesis is true. And finally, random noise can affect the p-value. A common example of random noise is a coincidence of random sampling. Did you like this video? Be sure to give it a like.
All right. Okay. So that is kind of like the overview of p-value. And I did say that it is equal to area under the curve, which is why the p-value will be between 0 and 1. Okay. So the smaller the p-value is, the better it is for us, meaning that there is stronger evidence against the null hypothesis, right? Because we want to go against the null hypothesis. We want to reject the null hypothesis, okay? So let's kind of go back to our problems to see what that actually kind of looks like with real numbers and a real problem, okay? So go back to the mini lecture, and I will also share my screen again. Okay, here we go. So you should see something like this. let's see. So instead of these examples here, go, what's it called? Scroll down and keep going till you see this highlighted in yellow part where it says back to our NBA example. Okay, so we're gonna stick to this problem for now before I introduce like a new problem. Okay, so let's finish up this problem. So remember that they have changed the rules so that they with a specific purpose to increase the scores. So what we did was we set up the initial conditions saying that the mu is equal to 183.2, which it means that before the rules have changed and after the rules have changed, nothing happened. Basically, the scores stayed the same, right? It's kind of like in the example in the video, it's like before taking drug X and after taking drug X, there was no difference in weight, right? It stayed the same. That's kind of like a similar situation. And then our alternative hypothesis in this particular context is that the mu increased, right? With the rules changed, we wanted to see an increase in score. So that's our alternative hypothesis. I keep like mixing up things. Okay, so we know that it's greater than this number, so it's going to be a right tail test. This is referring to when we do area under the curve eventually with a p-value. So we know it's a one-tailed test. So I might even say in here a one-tailed test, right? To kind of add more information. All right. So we're going to take these random samples. Remember, in this particular question, it gave us 25 data points, right? And with that information, remember earlier, I gave you the sample mean and the sample standard deviation, which you can also calculate using Google Spreadsheet. Okay, so this is our t-value equation. When you might remember this, but basically when the sigma is unknown, which is the population standard deviation, you will be using the t critical value. If the sigma is known, then we will use the z critical value. But in this case, we have a sample mean and a sample standard deviation. So this is the time to use a t critical value. And from above, this is the equation. So remember the sample mean that I gave you earlier, or if you want to do it by hand and try it out, you can select the 25 raw data points, and you can, calculate the sample mean. You can either literally type it in a calculator and then add them all up and divide it by 25, or you can select all of it and do equal average, and Google Spreadsheet will calculate it for you. So that number was 195.88. The null hypothesis was set to 183.2, so that was the average score for the NBA players. And then that's going to be divided by the sample standard deviation, which was also, I calculated that above for you, or you can select the 25 data points in Google Spreadsheet and do equal STDEV and make them calculate the standard deviation for you, right? So that was 20.27. And then remember, there was 25 samples that were provided in the question. So the N is equal to 25. So you plug that in and you are going to get this T critical value of 3.1275, okay? So that's the second part. We're not done yet. With 3.1275, you are going to try to find the p-value, okay? So there's two ways of doing it, okay? So let's start with using this particular website, which is called the p-value calculator. Where do you find that? Again, earlier, let's see if I can find it again. And you should save this as one of these bookmarks if you want, but I'll show you both ways how to calculate it and show you that you can get exactly the same answer, okay? So p-value calculator, where was it? Do you guys remember? I'll just search it. P-value calculator. No? Okay. P-value calculator. Here we go. So it was a little bit above, I think it was like page, is there a page number here? It's before where you see the little no evidence against null, some evidence, moderate, strong evidence. There's a p-value calculator given in this module. And then if you click on it, you're going to see that there's a link. Okay. If you click on that, you are going to get something like this. Okay. So what this is basically, it's just going to calculate this information for you very easily. So I'm going to go back to all the way down to where we were. Okay. So just now we calculate the t-score. So I'm going to plug that in and it's going to be 3.1275. Okay. Degrees of freedom, you might remember, but this is basically n minus 1. Okay. If you don't remember the concept, that's okay. But we did kind of see a video about it just to kind of see if that made sense. But degrees of freedom is n minus 1. So that's going to be 25 minus 1. So that's going to be 24. Okay. This significance level is something that that is always, it's going to be given to you in a question. And basically what it is that if I scroll up, it's going to be kind of like the threshold at which you can decide whether you have a lot of evidence or small evidence against the null hypothesis. And by default in the statistics community, we almost always use 0.05, okay? So you might remember, if I go all the way up here, because the smaller the p-value it is, it's better. So if it's like less than 0.05, that's always a good sign for you, right? So if it's between like 0.001 and 0.01, which is still very small than 0.05, you have very good evidence against the null. If it's even less than that, less than 0.001, then you have such strong evidence against the null, you can like really confidently reject it. The problem is when you have something that's closer to 0.05, right? Then it's kind of like moderate amount and like only some evidence against it. And if it's way bigger than 0.05, then you have really no evidence to reject the null hypothesis. So this is called something called a significance level, okay? So the significance level is usually decided at 0.05. So that's kind of like your little line where it says, okay, if it's below this, that's really good and you have a lot of evidence. If it's above this, you don't really have a good case here to reject the null hypothesis. And this has been used for decades and decades in the statistical community. It is actually, if you want to know, it is a contested topic. Like people are saying, well, it kind of seems like an arbitrary number to say that if it's less than this, it's good. And if it's like higher than this, it's not good. Because what if I got 0.051? You know, that's so close to that particular line. It's like, who are you to say that that's like really just not great, right? If it's that close. So it is a contested topic and a lot of people are kind of questioning the significance level that we've been taking as a default. But anyways, for our purpose, we don't have to get into like the whole academic discussion about it, but the significance level is always 0.05 unless stated otherwise in the problem. So sometimes you're not even going to see any mention about the significance level, then you just like default to 0.05, which is going to be most of your case, okay? And then the only thing, so this will just stay as is. The only thing you need to be careful is like you need to kind of look at your null and alternative and make sure that you are clicking the right one, whether it's one-tailed or two-tailed, right? In this case, we think the average score should be greater than 183.2. So it's a one-tailed test. So then after you have put the t-score, degrees of freedom, one-tailed or two-tailed, that information in, you're going to click calculate. And then at the bottom, it will give you a p-value of 0.002288, right? Which is a number that is very, 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 very lower than 0.05. And you can see that it even gives you, writes out that result, that the result is significant, right? It's very, very good because the p is less than 0.05. Right? A lot less. So this again will be strong or very strong evidence against the null hypothesis. So we can confidently reject the null hypothesis. I'm going to show you this. I'm going to show you this in Google spreadsheet, how that looks like. Oh, I should have opened up a Google spreadsheet right away. But if you want to do it, not use this particular interface, but want to use the Google spreadsheet interface, then this is what you will do. And in a second, it will be clear that you're using exactly the same information. So let me just open up a new spreadsheet really quickly. It's a little slow. If you already have a spreadsheet open, which you should always do, then kudos to you. I should have done this. Here we go. Okay. So what you're going to do is, and this information, is it in this document? Let me just really scroll quickly. It's not in this conversation. So if you go to our textbook, it will line it out for you. And we'll do this question in a second. But it's exactly the same. Hypothesis testing, the p-value. And the mini lecture information, you will see that all of this is also in the textbook too, okay? Oh, it's very, very slow. All right, so the way you are going to calculate the p-value is using this thing called t-dist, okay? And the numbers you plug in are exactly the same, okay? So let me just zoom in. This can respond. Okay, so what you're going to do is, this is how you calculate the p-value. You go t-dist because it's called a t-distribution, okay? So the very first thing you're going to put in here is your t critical value. I think that was 3.1275. So here you're going to put in 3.1275, comma, and then you see that it's degrees of freedom, which is the second one. And remember here, in the second box, you put in degrees of freedom. So it's exactly the same. So I'm gonna put 24 in there because there was 25 data points that was given in the MBA problem, and 25 minus 1 is 24. And then it tells you the tail test, right? Remember, you need to see if it's one tail test or two tail tests. In this particular case, the alternative hypothesis said greater than 183.2, so it's one-tailed. So then you know, instead of 2, you're going to put in 1 here, okay? So these are my 3 numbers that I put in. Remember, you don't have to worry about the significance level, usually, just like the same thing. This was defaulted to 0.05. This is the same for the t-dist equation. So again, once you're done with those 3 numbers that are put in here, you're going to click enter, and you will see that you get the exact same number, as in the exact same p-value, 0.0228, right? And in our mini lecture, which is, do I have that open here, right? In our mini lecture, 0.0228 is a very, very small number. I can go to there, 0.0228. Here we go, okay? So we know, so zoomed in quite a bit from that. All right, so we know that we use the p-value calculator, or just like I did, you use the Google spreadsheet t-dist function, and with the appropriate numbers, you get a p-score of 0.00229, okay? So the conclusion, because it is way, way, way less than 0.05, as a matter of fact, it's close to 0.001, you know that you have strong evidence against the null hypothesis, right? So you don't have to memorize any of this. You'll have that information, like maybe like a chart, to show you whether something is strong evidence against, very strong evidence against, moderate evidence against, or little evidence against the null hypothesis. But your kind of like abstract conclusion is that because this p-value lies between this, we have pretty strong evidence against the null. So we can reject the null hypothesis. This in turn, when you reject the hypothesis with strong evidence, this in turn is very strong evidence for the alternative hypothesis, right? It's very likely that the alternative hypothesis will be true. And that also means the average in this particular context of the problem, the average number of points scored is higher than what it was last year. Okay, so this means that the scoring changes have likely had the desired effect, and the average number of points scored per game this year seems to have gone up post the 1999-2000 season. Okay, so that is a full question we did together. I see that Mara, you have raised your hand.
Yeah, I just have a quick question. Is that, so I know that in this situation, rejecting the null hypothesis is strong evidence for the alternative hypothesis, but is that always going to be the case? Because like, could it possibly be like your null hypothesis is rejected, but then you're performing for like your alternative hypothesis, you're performing a right tail test, but it ends up like being that the left tail test is correct? I'm not sure if I'm saying this correctly, but like.
Okay, I think I know what you're saying. So there's no way. So when you set up the null and alternative, let's say it's like a left tail test, there's no way that would kind of flip to the right tail test. That will never happen. Okay, your initial setup with a null and alternative, that is your scenario you're dealing with, right? And yes, there's a case where you might strongly reject the null, but you might not strongly reject the null, right? You don't have a lot of evidence. So that means that, and it's like literally literal, it's no more than what it says. Either you have strong evidence to reject the null, so then the alternative is probably true. But if you don't reject the null, it only states that we can't confidently reject the null, so we can't also accept the alternative hypothesis. And if the alternative hypothesis is a left tail test, just because we can't really accept that, does not all of a sudden give us a different conclusion that, oh, well, because of that, it's a right tail. You don't flip to that. You literally take that conclusion and you just stay there. You don't add any added interpretation on top of that. You either reject the null or you fail to reject the null. And so in another section, and Amara, I think this is where you're going, there was a really good question asked to me in the other section where it said, okay, so if you don't get to reject the null hypothesis, which is what you were going for, then what do? Do you change your null and alternative, or do you do the experiment again? Like, what do you do? Okay, and that's a really good question. And that's what might be the question kind of you might be having, Mara. Well, that depends on the researcher's question, right? So for example, in the drug X example, let's say it was a weight loss drug X, they wanted to see that drug X actually worked, right? You can imagine in this particular, in our society where there's a lot of kind of bad media going on and certain body images are promoted more than others. So apparently like maybe weight loss is a thing that a pharmaceutical company would like to achieve and be successful at, right? So they like put in a lot of money and created the drug X, and they believe that it should work, right? Once you take this like drug X for, I don't know, 30 days, there would be weight loss. But they did the experiment and they didn't have strong evidence against the null, so they had to reject the null hypothesis, meaning that they couldn't really confidently say drug X worked, right? So then what? Well, there's many alternative things you could do. So like the video pointed out, maybe there was random noise. Somehow, by coincidence, we happened to get the testers with all high metabolism. So it showed good effect or it didn't show good effect. Or I guess in this case, I'm saying all of them had slow metabolism, right? So you don't know if that happens. So maybe you run another trial, right? You set the null and alternative exactly the same way, and you go for another like 30 people, 100 people, and you do that again, right? Or you do that several more times to see really if your first group of people were kind of like unique by coincidence, or this is actually what's happening, right? And maybe you do it 10 more times and you still got the same results. Then maybe you drop drug X and you put in money to develop drug Y and see if that's going to work. So depending on where you are as a researcher, you could keep doing the same experiment with the same null and alternative, or you ban that and you do something else, right? Because at the end of the day, you do want to have strong evidence to reject the null hypothesis. So if you think about what we are going through right now at this age, a lot of these pharmaceutical companies are doing these drug testing for the vaccine for coronavirus, right? And they need to be able to say with strong evidence that this vaccine actually will work for this demographic, right? They obviously want it to work for everybody, but maybe that's not showing enough evidence, right? Maybe there's some cases where they had a batch of 50 people and it showed some evidence that it was working, like after 30 days, an antigen was developed or the vaccine was working or they got over COVID, right? However, if there's not strong evidence for it, then you can't be very confident to distribute this drug to the entire world, right? This is a serious issue. So these are the steps that, you know, in real life, scientists do take to make sure there's highly, highly strong evidence against the null, meaning that your drug does work. So it's likely that it is going to work for a generic population or something like that. It's kind of a long-winded answer. Anyways, more questions? This is an excellent question because this is something that actually goes on in the real world and how it works, especially for drug companies. So, and that's why I keep giving you examples of drug X or drug A and B, because this is exactly the procedure they go through. And it's very relevant to us at this particular moment, isn't it? Okay, any additional questions about that? We're gonna now do another question so we can keep practicing. Okay, so if you don't have another question, go back to BB, content, hypothesis testing dash means, and you haven't done it in a while, but you're gonna see a Google spreadsheet. I think it's all the way at the bottom. Open up that Google spreadsheet. Again, you'll have only viewing privileges, so make a copy in your drive. And we're gonna do those questions. We're gonna start with the first question together. Okay, so I think each sheet is just one question. Okay, so let's start with the first sheet and we will solve that problem. And this is going to be walking through the steps of
Is it the handout?
It's not the handout, but if you have the handout open too, keep that open. We want to finish the handout questions as well, okay? We probably won't get to it today. So those will be homework. Well, I'll tell you the homework first, okay? So the homework is gonna be to finish all the questions in Google Spreadsheet, which I think is only 4 questions. There's 4 sheets and 1 sheet is 1 question per sheet. And then the handout from last week, which is still in the same place in Blackboard, we did the null and alternative, those 5 first questions. But if you go to the end of the handout, there's going to be 3 more questions, I believe. And those you have to finish. So in total, you're only going to be doing like 7 or 6 questions for homework, but each of them is to do all those 4 steps of hypothesis testing. And you'll have a full week to finish that, including the Thanksgiving break, okay? But let's start with the Google spreadsheet. So if you have found it, opened it, made a copy of that Google spreadsheet, and you're on sheet 1, write down spreadsheet in the chat so I know you're ready. And I will open that up too. So I thought I opened it up, but I don't have it with me. Oh, good. Spreadsheet. 3, 4, 5, 6, 7, 8. Okay, so go ahead and start the first question. I gotta find it. Where am I? Google Drive, yes. Google Drive.
I have a quick question.
Mm-hmm.
So the handout that we started last week, when we opened it, is it a document or is it a sheet, like a Google Excel sheet?
The one from last week is a Word document.
Thank you.
You didn't have access to a Google spreadsheet last week. And what I'm asking you to do now is open the hypothesis testing means assignment. That is a Google spreadsheet. And the first question should be about cola makers, like, you know, like Pepsi, Coca-Cola, that kind of maker.
Oh, thank you.
All right. So this is going to be similar to the MBA thing in that I'm giving you a few samples, 10 to be exact. And so you're going to have to find the sample mean using Google spreadsheet to, you know, do the test statistic part. But anyways, start with step 1 with the null and alternative hypothesis first.
Do you want us to write the steps in the spreadsheet or do you want just like the answer?
I would love you to write the steps. So, you know, there's a lot of room there. So you can say step 1, and then, you know, you should write out HO colon something, HA colon something, right? And then you should have a place where it says step 2, and maybe has, you know, you have a cell that says this is, you know, for T critical value colon, and then the next cell you can do equal, da, da, da. It's always good to have the steps laid out, right? And that will help you guys too, because then you'll have basically an answer sheet where it's like walking you through how to do this.
For the column makers sheet, I don't see like a hypothesis.
Okay, well, look at this. It says cola makers test new recipes for loss of sweetness during storage, right? And so you can see in the parentheses, it says the sweetness losses as calculated by sweetness before storage minus sweetness after storage. So then the question asks underneath the 10 samples, it says, are these data good evidence that the cola lost sweetness, cola did basically lose sweetness during storage? So this is one of those problems where you have to kind of extrapolate, infer a little bit to find out the hypothesis. So we're dealing with loss of sweetness in cola. So how would you set up the null hypothesis? This is a kind of like a tricky one. I put this on purpose because these are also questions that are asked often as well.
You would find the average first or find the mean of all of them?
Interesting. I guess your mind could go there. Anybody else? Anybody else has any guesses? So let me put it this way. By doing this experiment, if you will, we want to see if there's a difference before and after storage. Kind of like the MBA thing, after the rules change, is there a difference before and after? And the way it's, the scores are calculated, if you will, the sweetness scores, is that you have a number before and a number after and you subtract it. So if there's no difference before and after, what number would you get on the sweetness score? Let's say for some, yeah? Zero. Excellent, excellent. So this is a tricky one in the sense that I would set up the null as mu equals 0. Right?
I
Because
don't get that because that's not the mean of our.
well, this is a sample, right? But mu represents population mean. right?
Okay.
We don't know the population mean. We're always trying to guess the population mean, right? And we're as you can see, we're gonna do this experiment to like rate the sweetness before storage and say it's 3, 4, 5, whatever the scale is. And then after storage, we're gonna rate the sweetness, right? And we won't even be doing this if we were not even suspicious that some kind of change happens in terms of the sweetness. Like storage does have an effect on the sweetness. So if we look at the null, it's that there's no difference whatsoever before and after for anything, meaning that you tested every cola in the world and you rated the before and after, and they're always 2, 2, 3, 3, 4, 4, whatever. So when you subtract it, it's 0. So that the mean of all the cola sweetness before and after, when you average them, there's no difference, so it will equal 0. That is our null hypothesis, which is very unlikely probably, and we want to reject that. So in this particular case, the mu will equal 0 because mu is not the sample mean. You have a sample of 10 things that are happened here. And if you take the average of that, that's a sample mean, meaning that it's X bar. If the population mean is 0, then maybe X bar would have also been 0 too, no matter how many times you take the sample mean. But you know, that we also don't know either. But we are suspecting that it's not going to be the case that the sweetness is always equal in every case so that the population mean is 0. So we set that up as the null hypothesis because we want to reject that. So H0, I would say mu equals 0 in this case.
I have a question.
Mm-hmm.
So my first question is, if the population mean isn't provided, should we just assume that it's 0?
Population mean is never provided.
Right. Okay.
Right? So in the case of the NBA, what was provided was the average before the NBA scores average before the rules have been changed. So, you know, that's not like, okay, so in that case, you can kind of see that as the population mean given to you, I guess. So maybe Savannah's right. Like kind of like like almost like a crass way to approach it is that if a number is given to you, it probably won't state it as the population mean. So let's go to, maybe I can give you an example. So if population mean is kind of not going to give into you, but a number probably will be provided to you. And it's going to be that this is kind of like the claim of, what's the best way to describe this? Let's see.
In the question, it says the engines run for an average of 295 minutes. So like that would be technically the mu, right?
Yeah, so even that is actually not the population mu. It is an average of some sample usually. But we are saying that, so that's why that's why it's a claim that we think the population mu is equal to that particular average that was calculated. So everybody go to handbags. So that's the third sheet in Google Spreadsheet. It says that a manager this is about handbags. A manager feels the mean sales for all stores in the past year is less than $265,000, right? This is only the average of the sales from last year, right? That's not the population mean, okay? But we are gonna say the mu is equal to that one because if we were to have all the data in every year since the beginning of this handbag store, we are going to say it's equal to 265,000 because it's equal to last year's thing. So we're still making a claim about the population mean. So there's not going to be a situation it's going to specifically say the population mean is.
Wait, so for that question, the handbag question, it says the mean sales for all the stores in the past year is less than 265,000. So we use that, or do we use, okay, not the sample of 100 stores, right?
Well, the sample of 100 stores, that's your N. Okay, so all of those numbers is providing you information that you need to calculate in the process of hypothesis testing. The 265,000 is going to be what you claim is equal to the mu.
Okay.
Then at step 3, remember you have to do the T statistic. That's where you're going to use that sales mean of 255,000, which is the X bar. You're going to use N as 100, and then a sample standard deviation 57,000 is going to be the S. So you have all those numbers that you're plugging in. But still, to answer your question, the population mean is not 265,000. It is a average that is based on a specific sample, which in this particular case is the sales from the past year. And we are saying that that's equal to the population mean. We are claiming that this is true, which is probably not true. And then we don't want it to be true because we're trying to reject it.
Got it. Okay.
Okay, so let's go back to the cola makers. It is a little bit confusing. I do get that. So this is one of those questions that sometimes it will come up where you're not given a particular number about, you know, in the last year we tested so and so many colas before and after, and then we saw that the sweetness losses was about 3 or something. It didn't give you that information. And when those kind of problems come up, that's when you can kind of almost default to thinking, they're trying to say that there is some difference that will happen when storage happens. And so what we're trying to say that is there's going to be a change. So the change is going to be that it's not equal to 0, because 0 in this case means that whatever sweetness number you gave before and whatever sweetness number you gave after storage is going to be equal. So when you minus it, you're going to get a 0. Okay, the storage, it had no effect. That means if it was sweetness 2 before, after storage is also sweetness 2. So if you do 2 minus 2, it's 0. So we don't think that's going to be the case. And you can see from the 10 samples, it does seem like 0 never happens. Not that 10 cases is enough, but it does seem like there's always going to be some kind of difference. So you want the null to be that there is no difference, so 0. And then you want the alternative to be like, no, it's not equal to 0, meaning that the before and after there is going to be some change.
Got it. So this one would be a two-tailed test, right?
Exactly. Yes. Excellent. This will be a two-tailed test. So when you do the t-dist, for example, the last number will be 2 instead of 1. Or if you're using that P calculator interface, then you will have to click on the two-tailed thing. Mara, do you have another question?
Yeah, I was just wondering, like, I'm setting up the T equation right now, and I just want to verify if my numbers are correct. For the data value, you would input that as 0, and then the mean would be the sample mean.
Oh, so the T value, yes. So X bar is the sample mean. So that's the first one you put in. So that number minus 0 in this case, because that's our null, divided by the standard deviation, which is 1.196, which is given to you in the question, divided by a square root of n.
Yeah,
Okay.
So I was just wondering.
Morgan, you have a question?
I don't understand the double-tailed thing. So are we taking, does that just mean we're taking 2 random samples?
No, this just means that when you were drawing a distribution, so for example, let me just draw this. That just literally means, like, if I had a drawing like this just means that what at the end, the area we're calculating is going to be that end and that end together. Oh, you can't point to it. So we're calculating 2 areas. That's what it means.
No, what? By finding the T value? That's what we're doing?
By finding the P value. Remember, P value is equivalent to the area under the curve. And just based on the question, it just happens to be that it's not a right tail or left tailed, so it's a two-tailed test.
Because the HA is
Not
equal is not equal to, okay,
Correct.
not equal to.
correct.
Okay.
Yes, yes. So this area, no.
So for this question, what would be the X bar and what would be N?
Give me 1 second. Okay, so I don't want to add confusion, but this is kind of how it's defined. So that middle area that's not colored is the area where we reject the null. And that's very high, right? It's like the majority of the area under the curve. So that's good. That's the probability that we're going to reject the null. And then the probability that we fail to reject the null are these two edges. So remember, probability, we're dealing with numbers at 0 to 1. We want to be able to reject the null hypothesis with high confidence. So that means that middle area is going to get bigger and bigger and bigger, and the tails are really small, right? So that's why we have this significance level, and it's like, oh, is it 5% of the time we're going to fail to reject it, or is it like 0.01% or 1% of the time, or 0. Whatever, any number, this much time are we going to fail to reject it? We want to make sure, we want to always have a result where we fail to reject the null hypothesis as small as possible. But depending on the question, how we initially set up the null or alternative, we are going to either have that fail to reject the null is going to be either two areas under the curve, or it's just going to be one side of the curve. And we want that to be as small as possible, but that always depends on the context of the question. Okay, so Deidre is asking, and I think that's similar to another question that was going to be raised. You don't understand how to the equation set up. So the equation, you don't have to understand the equation. The equation is just there. All you got to do is you got to plug in the number. So in this particular case, guys, what is the sample mean? It's not given to you, so you have to calculate it. That's why I'm telling you this is similar to the MBA problem. So what did people get for the sample mean? Okay, Savannah got 1.02. Did people get the same?
I got the same thing.
Okay, good, right? So you select the 10 cells and do equal average and you get the sample mean. Usually the question will give it to you, like the lawnmower, handbags, and academic performance one. But sometimes they might just give you the raw information and you have to calculate it from there. So then, Deidre, all you got to do is plug it in. 1.02 minus 0 divided by 1.196 divided by the square root of 10. Okay, Savannah, you raise your hand.
If the sample standard deviation isn't provided, it's just equals STDEV. It doesn't change anything because it says sample when we're calculating it in Google Sheets, right?
Well, it is given to you in this question. It says sample standard deviation is 1.196, but you can go ahead and do equal STDEV and you will get the same number.
Okay, just for the problems that they don't provide it.
Correct, yeah. If they don't provide it, then you select those and you do equal STDEV, yes. And remember, you don't have to necessarily remember that exact equation, right? That information is available to you, but that's just the information we did way in the beginning. But the final is a cumulative, right? So you do need to kind of have this in your notes somewhere to refer back to it. Yes, Mara.
Okay, I finished the problem and I got a really high p-value. Except,
okay, so let's discuss that.
Yeah.
What did people get for their p-values? What did you get, Mara?
0.4158888.
Okay, so Mara got 0.4188888. What did other people get?
I
Okay.
got 0.0245.
Okay. Do we have other answers? It seems like we have maybe two kinds of answers.
Well, okay, when I plugged mine into the p-value calculator, I selected like two-tail, like because you can like you can change, what's it called? It asks if you're doing a one-tailed or two-tailed hypothesis, so I selected two-tailed.
Okay.
Is that going to change anything, or is it? Like,
Well, it should, and you did the right thing. It is a two-tailed test, so it will give you a different answer than a one-tailed. So that's good. It seems like you might have inputted, so you're using that p-value calculator thing?
Right.
Okay, so what did you put in for your t critical value?
My T critical value was 0.8528.
I actually don't have my t critical value. Is that what people got for their t critical value?
No, I got something different.
Okay, so you probably calculated it wrong.
Okay.
Yeah.
So for my For my T value, I put open parentheses 1.08 or 1.02 minus 0 close parentheses divided by 1.196, which should be correct.
Hold on. If you say a lot of numbers, it's gonna, I can't remember all of it. So let me just share my screen.
Yeah.
Okay, so I'll do it both ways.
I think what happened was Mara just put like divided by the standard deviation rather than it's supposed to be the standard deviation divided by the square root of
Square
n.
root of n.
Yeah.
Oh, okay. Yep. Got it.
Okay, so I'm gonna go with your numbers, guys. So I'm gonna here t critical value. I'll just write it out here. And maybe I can like zoom in a little bit so it's a little bit easier to see. Okay, guys, so I have the question here, and then this is a t critical value. So I'm gonna go ahead and do equal right here, okay, guys? And I'm gonna use the numbers you gave me. 1.02 you said was the X bar, correct? Then I'm gonna do minus 0. That's at the top. And then I'm gonna do divided. And I'm gonna go ahead and open up and close parentheses for the bottom, the denominator, okay? And I know the top one was sample standard deviation, which is given to you right here, 1.196. So 1.196 divided by square root, open and close parentheses, square root of 10. Remember, we gave 10 tasters. This is the n. So that is all closed properly. So then I'm gonna do enter, and I got 2.6969. And then for the p-value, I will do p-value. I'll do it both ways. I'm gonna do it here and t dist, right? If I wasn't clear before, and make sure please refer to the example that's given to you in your textbook. 24.3 in the examples it gives it to you, but it is the absolute value of your t critical value, okay? So that's always gonna be a positive number. But anyway, so you do ABS, so I'm gonna do ABS, and then I'm gonna close that one. And in here, I'm gonna go ahead and just keep the original t critical value, so I'm just gonna click on that, okay? So that's my first number. And then after that, after the parentheses, comma, n minus 1 is degrees of freedom. So that's 9 because it's 10 minus 1, comma. In this case, it's not a one-tailed, but it's a two-tailed. So I'm going to put 2 in. And then I'm going to do enter. Okay, so that's what I got, 0.025. I'm going to also go ahead and use that p-value calculator to show you the same thing. Do I have it open? Yes, I do. That's great. So I'm going to go ahead. And where is all my, okay. So I'm gonna have that spreadsheet open. So my t-score was, I'm gonna try to keep it as much as I can, 2.69692. It doesn't let me do more than that, so I'll keep that there. Degrees of freedom is 10 minus 1, so that's 9. Significance level as is. It's not one-tailed, it's two-tailed. So now I'm gonna calculate. And you will see that I got the exact same number as I did here, 0.0245. And then you can see that the result is significant in less than 0.05. So I have strong evidence to, or I have strong evidence to reject the null. So in this case, I thought we set it up that the null was that there was no difference before and after storage. So since I have strong evidence to reject it, my conclusion, which is also what you should write here, is that there is good evidence that after storage, the cola will have some kind of difference in the sweetness, right? We set it up as not equal to. if you set this up, because I said evidence that the cola would lose sweetness, if you said less than 0 and you did one-tailed and you said there is strong evidence that you do lose sweetness, I will also mark that as correct, okay? Because I can see this going in two different directions. Either it's like not equal to 0, or because this does say lost sweetness, so it's less than 0. That meaning that the direction of the sweetness goes in a negative direction.
Professor, I have a question on the conclusion though.
Okay, sure.
Because so the calculator, yeah, I got that as well. Like I got all of those numbers, and it said strongest, but in your Google document where you have all the steps listed, it says any p-value between 0.0 and 0.05, then moderate evidence.
Didn't we get 0.0245? So that's less than 0.05.
But it's between, yeah. So it's between 0.01 and
it's between 0.01 and 0.05. Right?
Yeah. And that says moderate. Yeah.
So then the conclusion is there's moderate evidence against the null hypothesis. Okay, maybe I got that wrong.
But it says, it doesn't say that on the calculator. I don't know.
Oh, I see. Yeah. It should be, if it's lower than 0.05, it's usually strong evidence against it. Let me just go back to double, triple check. And I'm just gonna go to this Google Docs. It says, very much zoomed in. I'm pretty sure it should say strong evidence. Not very strong evidence, but like strong evidence.
Yeah, so it says strong evidence is between 0.001 and 0.01.
Okay, all right. So there's moderate evidence against it, I guess. Let me just double check that with the chapter. I guess the mini lecture is a little bit, let's see. Okay, yes, you're right. You're right, Morgan. We did write that it's moderate evidence against the null. So the most accurate statement should be there's moderate evidence against the null hypothesis.
Okay.
From my research, that's pretty strong evidence, but that's fine. That's fine. Moderate is fine. If you said moderate or strong, either one should be correct. These are kind of like qualitative analysis, if you will, which is, depending on which researcher you ask, they might say, oh, that's moderate or that's strong. So whatever guideline I gave you, if you follow that, that's absolutely fine. Yes, moderate is good. Okay. Oh, guys, it's time. Okay, so just know there is class on Wednesday, and even though it's the day before Thanksgiving, I didn't realize. Somebody was asking, do we have class on Wednesday? I'm like, yes, it's Wednesday. Anyway, so we have class on Wednesday. But the homework to finish this Google spreadsheet and to finish the handout from last week, the Google, the Word document, there's only 3 extra questions all the way at the end. That's all you need to do. Don't worry about the type 1, type 2 error. Those 3 questions and these 4 Google spreadsheets. So 7 questions, you have a full week to do it. So that's going to be due next week, Monday at like 12 p.m. or something like that. Oh, Jenny, no, I did not mark you as present. Hello. Okay, so let me know if you joined, but other than that, you are free to go, and then I will see you Wednesday.
Thank you.
Thank you. The final for this class is the last Wednesday, which is, and we'll cover that, which is December 9th, guys, December 9th.
Okay, thank you.
Okay.
Thank you.
Yes. Jenny. Okay. All right, done. Emma and Alexis did not come, I think. All right, see you, Jenny.